I'm Bobby Scott. I'm going to speak to you today about low-dose radiation-activated natural protection and evolutionary gift. Life on Earth formed many years ago in a high natural radiation environment. As a result of that, there's an evolutionary process that has taken place that has led to the development of natural protective processes in the body. These processes are activated by low-level radiation. I refer to that as activated natural protection. The activated natural protection system includes multi-levels from the molecular to the cellular to the tissue and organismic levels. These include DNA repair, apoptosis of severely damaged cells, a specialized apoptosis process which is epigenetic. We call it apoptosis. It relates to removal of precancerous and other aberrant cells from the body. These are triggered by low-dose radiation, especially by what we call low LET radiation. Examples of low LET radiation are gamma rays, beta rays, and X-rays, such as are derived from CT scans and other diagnostic procedures. Some components of protection, this natural protection, may have been switched off many years ago during the evolutionary process as the natural radiation environment declined. The very high radiation doses relative to the radiation doses many years ago when mammals were evolving, radiation doses very much higher than those can turn off genes, silence genes. The natural system is very effectively activated by X-rays, gamma rays, beta radiation, not very effectively activated by alpha radiation. However, if you have a combination of both the low LET beta, gamma, or X-rays with the high LET alpha, the low LET component can activate natural protection and actually suppress cancer induction by the high LET alpha radiation. The differences between the high and low LET radiation may relate to how the microscopic energy depositions take place in the cellular environment. At the level of the cell, radiation dose deposition is stochastic. For alpha particles, the spatial distribution is different from what one gets for X-rays or for gamma rays or beta radiation, where they're more dispersed relative to the tissue. Alpha particles are tightly clustered. Their ionizations are tightly clustered. And this may have an impact on the intercellular signaling, explaining the differences between the lack of activation of protective signaling pathways by alpha particles and more efficient activation of these signaling pathways by the low LET beta, gamma, and X-rays. The original basis for the risk assessment policy of using a linear no threshold risk model was based on early studies in fruit flies. These studies use relatively high doses and high dose rates. More recently, a group in Japan added lower doses, very low doses, less than 100 milligray. And as a result of those studies, there was an adaptive response, a hormetic response, U-shaped, not a linear dose response curve at these very low radiation doses. So these very low radiation doses were protective. The original basis for the linear no threshold risk model being the mutation studies these new studies therefore invalidate the use of LNT for mutations based on fruit flies. Current practices of using linear no threshold for risk assessment is largely based on epidemiological studies. These studies are seriously flawed. They use procedures, methodologies that distort the shape of the dose response curve. One of these procedures is called dose lagging. This is where one throws away a portion of the dose. This shifts the dose response curve toward the left. Another procedure is averaging over wide dose intervals. This takes away hermetic characteristics of dose responses or threshold characteristics. And so, given these new understandings, it is no longer justifiable to use the linear no threshold risk model for low dose radiation risk assessment. Thank you for your patience.